One of the central questions regarding Ceton sets is the following. What is the largest size of a Ceton set? What is the largest size of a Ceton set S, where S is a subset of the natural numbers up to n? And we're going to denote this largest size, for reasons that will become clearer later on in this series, as f sub 2 comma 1 of n. So this is defined to be the maximum size of a Ceton set, where this Ceton set lives in the natural numbers up to n. And we can actually obtain an upper bound on this value by observing that if A is a Ceton set, then the set, or rather the size of the set of all multi-subsets of A of size 2, this set, or the size of the set rather, is exactly the same as the set of all sums of 2 elements from A. Note that A plus A is just shorthand for the set of all sums of 2 elements from A. And so to prove this, we can create a bijection between these two sets. Let's call this set X and this set Y. And this bijection, so F sends elements in X to elements in Y, is defined to be the following. So it sends a multi-subset of A of size 2 to the sum of the elements in that multiset. And so to see that this map is surjective, let's take an element X in A plus A. Then this implies that X is equal to A1 plus A2 for some A1, A2 in A. And it's clear that there exists a multi-subset of A of size 2 that contains A1 and A2. So F of A1 and A2 is equal to X. So this shows surjectivity. To show that this map is injective, then let's take the image of 2 multisets and suppose that these images are equal. So F of this multiset is equal to F of this multiset, both of size 2, of course. And if this happens, then this means that A plus B, this implies that A plus B is equal to C plus D. But this implies, because A is a Ceton set, that the multisets A and B, A comma B, the multiset A comma B, is equal to the multiset C comma D. So F is injective, and this completes the proof that F is a bijection. And by a stars and bars argument, you can prove that the number of multi-subsets of A of size 2 is the size of A plus 1, choose 2. And let me give a quick sketch of this argument. So if A was equal to, say, for simplicity, let's just say 1, 2, 3, and 4, then the number of multi-subsets of A of size 2 is exactly the number of ways to arrange 2 stars in 3 bars. So if I have 3 dividers, then the space in between each divider represents one of the elements 1, 2, 3, and 4. So let's say this is 1, 2, 3, and 4. And the number of bars, the number of stars within each divider represents the multiplicity of that element. So this arrangement of stars and bars represents the multiset 1, 1. And the number of ways, so notice that there's 5 positions here, 1, 2, 3, 4, and 5. And so the number of ways to arrange 2 stars in 3 bars is completely dictated by how many ways we can place 2 stars in 5 positions, 5 blanks here. And that is counted by 5 choose 2. And so this is a quick sketch of why this is the number of multi-subsets of size 2 from A. That is, it's the number of multi-subsets of size 2 of elements of A. And check this out. Check this out. We know that A plus 1 choose 2, this is equal to the size of A times the size of A plus 1 over 2. And moreover, we know that this guy is equal to the size of A plus A by the bijection argument that we just showed. And also, since A plus A is a subset of the integers 2, 3, all the way up to 2n. And so this means that the size of A plus A is at most 2n. So check this out. Check this out. This tells us that A, the size of A, times the size of A plus 1 over 2. Well, this is less than or equal to 2n. And notice that we can say that for simplicity's sake, this is greater than or equal to A squared over 2, which gives us that the size of A is bounded above by 2 square root of n. And thus, the maximum size of a Ceton set in the integers up to n, in the positive integers up to n, is bounded above by 2 square root of n.